On May 26, 1919, at the Farnborough Airfield, an experimental aircraft of massive proportions was being prepped for its maiden flight. Sitting on the runway was a triplane as tall as a multi-story building. The plane was equipped with 6 engines and 3 wings. Pilots Frederick Dunn and Peter Rawlings took their seats in the open cockpit, while 4 crew members settled inside the fuselage to monitor the onboard systems. Once all the power plants were fired up, the takeoff run began. At first, power was applied to the 4 lower engines. As the tail lifted off the ground, the pilot throttled the 2 top motors to full power. The sudden torque caused the aircraft to pitch forward violently. The landing gear struts collapsed and the fuselage nose slammed into the earth. Both pilots were killed in the crash. The 4 crew members inside the fuselage survived. One escaped through the tail section with a broken leg. That marked the end of testing for what was then the largest bomber in existence. The project had emerged at the end of the First World War, alongside the development of the British Handley Page heavy bomber designed for long-range missions. Even though the fighting had stopped, the concept of a strategic bomber remained a priority for design bureaus. The driving force behind this new project was an entrepreneur named Walter George Tarrant. Tarrant owned a company in Surrey that specialized in woodworking and construction. During the war, his factory produced structural components for aviation, including patented wooden spars. By 1917, the industrialist decided to shift from making parts to building a complete aircraft, one designed to outperform anything else in the sky. To make it happen, he assembled a team of engineers, joined by Belgian designer Marcel Lobel and William Barling from the Royal Aircraft Factory. Initially, the design called for a 4-engine biplane. The plan was to use 600 horsepower Siddeley Tiger engines arranged in tandem pairs, but technical issues with the engines forced a revision of the project. They decided to alter the design, opting instead for 6 Napier Lion engines, each producing 450 horsepower. To accommodate the extra power plants, a 3rd wing was added to the airframe. The central wing had the widest span, while the top and bottom wings were smaller but identical in size. The power setup included 6 engines. 4 were arranged in tandem pairs between the bottom and middle wings, while 2 single motors sat between the middle and top wings. A mix of 4 tractor and 2 pusher propellers was used to generate the necessary thrust. To keep the massive structure rigid, engineers used a system of diagonal struts running from the top wing through the center down to the fuselage, creating a worn truss. The aircraft was developed as a strategic bomber with a calculated payload of about 20 105-kilogram bombs, totaling more than 2 tons. The ordnance was mounted under the central section of the bottom wing, distributing the weight across the entire lifting structure rather than just the fuselage. The fuselage was built using a patented technology, a streamlined monocoque assembled from circular frames and stringers, then skinned with plywood 2 to 4 millimeters thick. This design was intended to provide a combination of lightness and strength. The biplane-style tail section consisted of 2 horizontal stabilizers. The lower one was equipped with an elevator, while the upper one featured a trimmer adjustable from the cockpit. An additional elevator was positioned between the stabilizers. Significant attention was paid to longitudinal stability, since mounting the top engines shifted the center of thrust well above the center of gravity, creating potential risks for control. The chassis featured a complex technical design. 2 main support structures each carried 3 wheels, 1.5 meters in diameter, mounted on a common axle. The landing gear assemblies were attached beneath the engine nacelle struts, which allowed the shock of landing to be distributed across the wings and their structural elements. The wheelbase was nearly 9.5 meters wide, intended to ensure stability while taxiing. Construction wrapped up around the middle of spring 1919, though sources disagree on whether there were work stoppages. Because of the aircraft's sheer height, final assembly took place in a dirigible shed at the Farnborough Airfield. Moving the finished machine in and out of the hangar had to be done sideways along specially laid railway tracks. By May 1919, the prototype was prepared for demonstration. The central wingspan reached 40 meters. The fuselage was 22.5 meters long and the height exceeded 11 meters. These dimensions made the craft taller than the Italian Caproni CA-90, which was considered one of the largest biplanes in aviation history. The aircraft's crew was supposed to number 6 men, including 2 pilots. Existing documentation lacks data on defensive armament, but it is assumed the team included a bombardier and a flight engineer responsible for monitoring the 6 engines. The cockpit was open while the rest of the crew entered the fuselage through 2 hatches located under the nose section. Flight tests had not been conducted, so the machine's performance characteristics remained theoretical. Wind tunnel testing on a model was performed by specialists from the Royal Aircraft Establishment and the National Physical Laboratory. According to their data, the top speed could exceed 170 kilometers per hour. The service ceiling reached 4,000 meters and the estimated flight duration was about 12 hours. For heavy bomber aviation of that period, these were impressive figures. However, the conclusions of the 2 organizations differed on a crucial point. The Institute pointed to an excessive tail-heavy center of gravity, while the laboratory disagreed with this assessment. To correct this supposed flaw, it was proposed to place a 1-ton lead ballast in the nose. The designer, Tarrant, objected to this change, believing the Aviation Institute's conclusions were incorrect. Despite the developers' objections, the ballast was installed. There is no reliable information on whether Tarrant himself or the assigned test pilots were notified of this decision. This circumstance would subsequently influence the events that followed. Preparing for the first flight was a laborious process. Starting 6 engines presented a complex technical challenge. Engineers had to erect a massive scaffold and use one of the largest mechanical huck starters available. The device sequentially spun the engine shafts until they ran on their own. The roar of 6 engines, each with 450 horsepower, could be heard across the entire airfield, attracting the attention of observers and the press. Captain Dunn performed several trial runs to check ground handling. The 6-wheeled landing gear supported the structure's weight, and the control surfaces responded to inputs. The situation was assessed as the triplane being ready for a takeoff attempt. Having received clearance for takeoff, the pilot began the run. The throttles of the 4 lower engines, nestled between the bottom and middle wings, were gently opened. 2 tractor and 2 pusher propellers began accelerating the heavy machine across the airfield's grass. Speed increased gradually. The massive 5-foot wheels gained momentum, leaving tracks in the soft ground. When the craft reached the necessary speed, the tail section started to lift and the triplane leveled out. At that moment, the pilot took an action that determined the outcome of the test. He abruptly pushed the 2 upper engines mounted between the middle and top wings at a height of 28 feet to full power. The power plants generated significant thrust at the highest point of the structure. Physical forces caused the aircraft to lose stability. The upper engines instantly created a significant overturning moment relative to the wheels. The nose of the machine jerked upward, the front landing gear struts lifted off the surface, the center of gravity shifted forward, and the heavy triplane crashed down onto its nose. The gear struts couldn't withstand the load and collapsed. The front section of the fuselage struck the ground, deforming and shattering. The cockpit was buried under the wreckage. Captains Frederick Dunn and Peter Rawlings were killed instantly by the collapsing airframe. The bodies of the deceased were recovered from the wreckage several hours later. The tail section of the aircraft had risen high into the air, causing the crew members in the rear to experience significant G-forces. Captain Thomas Wilson was thrown through the rear section of the fuselage. He hit the ground and broke his leg. 3 other crew members survived, suffering from bruises and shock. There remained a danger of fire due to full fuel tanks and running motors. One of the men on board managed to reach the master switch and cut the aircraft's electrical system. This action prevented ignition and potential further casualties. The engine stopped and a fire never started. A rescue operation began at the crash site. The investigative commission worked for several weeks, studying the debris, interviewing witnesses, and analyzing documentation. It was determined that the immediate cause of the accident was engaging the upper engines at full power before the aircraft had gained enough speed to lift off. The high placement of the motors created a pitch moment that the elevators could not compensate for. Investigators also discovered that a ton of lead ballast had been installed in the nose, a fact the pilots were likely never told. Had they known about the extra weight, they might have managed the engines differently. The aircraft was flying with a minimum load. The center of gravity was shifted further forward than the crew assumed, and firing up the upper motors led to a critical situation. The investigation revealed design flaws. Placing powerful engines at such a height created risks of control loss. Technical disagreements between specialized institutes regarding the center of gravity were not properly resolved, and adding ballast without notifying the crew was ruled a fatal error. The incident received wide press coverage, sparking criticism of the very concept of such massive aircraft. For Walter Tarrant, the loss of this unique prototype meant the effective end of the project. After the disaster, engineers and representatives from the military department held a meeting to determine the future of the project. The technical plans for building a second unit were already prepared, and the intention was to make changes based on the experience gained. Specialists also considered the possibility of adapting the design for civilian use, since in the post-war period Britain had a need for transport aviation to carry cargo and passengers. The significant internal volume of the fuselage theoretically allowed the triplane to be used as a commercial airliner. However, engineering analysis revealed critical flaws. Experts concluded that the aircraft was fundamentally unstable. Placing engines on 3 levels created substantial control problems. Any lack of synchronization in the engines or inaccuracy in piloting could lead to an emergency situation. The top engines created significant leverage, increasing the risk of the machine tipping over. Modification options were proposed, the most radical of which was dismantling the top wing and 2 motors. Converting the triplane into a biplane would lower the center of thrust and improve handling, but this would lead to a loss of lift. The 4 remaining Napier Lion engines, with 450 horsepower each, might prove insufficient for the flight of such a heavy aircraft. The option of replacing the main engines with more powerful ones to compensate for losses was also considered, but financial calculations showed that continuing the work was impractical. The cost of modernization was estimated to be prohibitively high. It required not just dismantling a wing, but a complete redesign of the propulsion layout, recalculating the balance, creating new assemblies, and testing the updated structure. In fact, this implied creating a new aircraft that only partially resembled the original project. The government, in the conditions of the post-war economy, did not plan to invest funds in a high-risk project. The military department had lost interest in strategic bombers after the end of combat operations, and civil aviation needed a different type of machinery. Walter Tarrant faced a choice. Continuing work required investing personal funds with an uncertain result, and the company's reputation had already suffered after the death of the 2 pilots. Abandoning aircraft construction meant closing a division into which resources had already been invested. After a comprehensive assessment of the situation and consultations with engineers and financial advisors, the final decision was made to end the project. Construction of the second unit was canceled, and aviation operations were wound down. The company returned to its main specialization, the production of wooden structures and construction contracts. The participants in the development, including Marcel Lobel and William Barling, returned to their previous activities. The airship hangar at Farnborough was vacated. The wreckage of the triplane was scrapped, the railway tracks were dismantled, and the equipment, including the Huck starter, was sent to storage. This event marked the end of Walter Tarrant's sole attempt to break into the aviation industry. His company kept working in the construction sector, but it never returned to designing aircraft. The engineering team involved in the project moved on to other specialized organizations, taking with them the experience and lessons learned from this failed experiment. Moving forward, British aviation shifted its focus to building aircraft of more moderate dimensions, prioritizing reliability and handling over sheer size. The story of the triplane became a cautionary tale for the industry. It demonstrated that increasing scale and power doesn't always guarantee success, and that the physical limits of design simply cannot be ignored. May 26, 1919 went down in aviation history as the day Britain lost its largest bomber of the First World War era, a giant that was destroyed before it ever really got off the ground. An expert commission conducted a detailed study of the crash, leading to a change in test flight regulations. New requirements were introduced for extensive ground checks. including handling tests under various engine settings. Pilots were now required to study the design features and equipment layout in detail. Documentation standards were tightened, and personal responsibility was established for ensuring the crew was properly briefed. Technical specialists also concluded that engines on multi-engine aircraft needed to be placed closer to the center of gravity, ensuring they could be engaged smoothly and in sync. The layout featuring engines mounted at vastly different heights was deemed ineffective and was never used again in mass production. Operations at Farnborough Airfield gradually returned to normal, though the incident left a mark on the memories of those who saw it. The technical staff involved in prepping the flight felt a heavy psychological burden, even though they hadn't made any mistakes. Witnesses described the moment of the crash as the massive machine lurching sharply nose forward before slamming into the ground. It served as a stark reminder of the high risks in aviation and the fine line between success and failure. Government compensation was paid to the families of the deceased captains, Frederick Dunn and Peter Rawlings. Both of the fallen airmen were qualified military pilots with First World War experience. Having survived combat missions and emergency situations in the war zone, they lost their lives testing equipment in peacetime. They were buried with full military honors, and their names were added to the roll of those killed in the line of duty. Captain Thomas Wilson, who was thrown clear through the rear of the fuselage, spent several months in the hospital. After recovering from a broken leg, he stopped flying, left the military service, and took an administrative position within the aviation department. The 3 other crew members suffered bruises and shock. The incident forced them to reevaluate the risks involved in testing experimental aircraft. Marcel Lobel returned to the continent, continuing his engineering work in aviation in Belgium and France. He applied the experience he gained from the heavy triplane project to his later career, though he preferred not to dwell on the Farnborough incident. William Barling stayed on at the Royal Aircraft Factory and worked on a number of interwar projects. In his professional life, he began prioritizing comprehensive testing, refusing to get involved in work where the technical risks weren't sufficiently justified. Walter Tarrant's company carried on in the construction sector, handling major contracts and supplying industrial structures. Yet, in aviation history, his name remains forever linked to the events of May 26, 1919. It's said that the entrepreneur took the tragedy hard, but he refrained from discussing it publicly. The aircraft itself was lost completely, the wreckage was scrapped, and the technical records were either partially destroyed or filed away in archives. No fragments of the machine survive to this day. The only proof that this machine even existed lies in archival photos and the official investigation files. The pictures show a craft with 3 wings and 6 engines sitting outside the hangar, waiting for tests. The British aviation industry took the results of this experience to heart. Designers began showing much more caution when choosing aerodynamic layouts and evaluating the consequences of their design choices. The concept of placing engines far apart vertically was deemed ineffective. Military clients tightened their requirements for justifying non-standard technical solutions, and the approach to funding experimental projects became far more pragmatic. The incident demonstrated that increasing the size and power of a machine has its operational limits. Throughout the 1920s and 1930s, aviation evolved by refining aerodynamics, improving materials, and increasing the reliability of components rather than simply making things bigger. The design of subsequent large aircraft took the negative experience of the Farnborough triplane into account, helping to avoid repeating those mistakes. The story of this plane is seen as a prime example of the technical risks that arise from a lack of empirical data and overconfidence in unproven concepts. Walter Tarrant's ambition to create a unique machine faced objective difficulties. Despite the engineer's efforts and the crew's readiness, a combination of factors, including layout errors and communication problems, led to the emergency. The prototype never made a full flight, and the disaster resulted in the death of 2 pilots. This case serves as an illustration of the importance of adhering to basic physical principles and the dangers of haste in aircraft construction. The events of May 26, 1919 remain a tragic episode in history, but the technical analysis of the crash helped raise safety standards, Conclusions drawn from studying the accident influence the future development of the industry and help minimize risks in future designs. This historical example shows how analyzing failed projects becomes part of the knowledge base necessary for the evolution of engineering thought and the prevention of similar incidents.